Ever think about what protects your bank account or your private messages? Almost every single part of our digital lives is shielded by a secret code. It's the very bedrock of our modern world. But a completely new kind of computer is on the horizon, and it threatens to shatter that foundation to pieces. So yeah, let's dive right into this quantum security dilemma.
All right, here's the game plan for this explainer. First, we're going to get a handle on the quantum threat itself. Then we'll explore two totally different solutions. One's all about new math, the other is about new physics. We'll put them head to head, and finally, we'll look at the very real, very intense race to build these incredible machines.
Okay, first things first. Let's start with the problem. Why exactly is our entire digital world kinda on the brink?
I mean, seriously, think about it for a second. Every single time you send a message, log into your bank, or buy something online, there's this invisible shield at work. That shield is cryptography. It's the secret sauce that makes the whole modern internet even possible, keeping our information private and secure.
And this is the question that keeps security experts up at night. What happens if that invisible shield just breaks? What if the very foundation it's built on is about to just crumble?
So, here's the crucial thing to understand. Our current security is what you'd call security through difficulty. It's not that the math problems protecting us are impossible to solve. They're just ridiculously, mind-bogglingly hard. A normal supercomputer would need literally billions of years to crack the codes we use today. So, we feel pretty safe.
And then, along comes the villain of our story, Shor's algorithm. A mathematician named Peter Shor dreamed this thing up way back in 1994. And what it does is pretty terrifying. It takes those ridiculously hard problems we just talked about, and for a powerful quantum computer, it makes them easy. For a machine like that, our digital locks might as well be made of paper.
So, if the old locks are about to get broken, what do? You build better locks, right? And that brings us to our first potential solution, post-quantum cryptography, or PQC for short.
The idea behind PQC is actually pretty straightforward. It's like, okay, so quantum computers are great at solving our current math problems. Fine, we'll just invent new math problems that are hard for everybody, including them. It's basically a massive software patch for the entire internet.
So instead of relying on the old trick of factoring large numbers, PQC is all about finding completely new kinds of mathematical puzzles. Take something like lattice-based problems. Just imagine trying to find the shortest, most direct path through a giant, super complex, multidimensional grid of points. Sounds tough, right? Well, it's believed to be incredibly hard for any kind of computer to solve, classical or quantum. And that is the new kind of lock.
Now let's look at a completely different way of thinking. Instead of building a stronger lock out of math, what if we could use the fundamental laws of physics as the lock itself? Now we're getting into some wild territory. This is the whole idea behind quantum key distribution, or QKD.
You see, QKD is playing a totally different game. It's not about a problem being hard to solve. No, its security comes straight from the laws of quantum mechanics. This gives us something called information theoretic security. And that's just a fancy way of saying it is perfectly, unconditionally secure. It literally doesn't matter how powerful your computer is, you can't break the laws of physics.
So how on earth does that actually work? Well, to get it, we need to meet the classic cryptography crew. We've got Alice, who wants to send a secret key to Bob, and then there's our villain, Eve, the eavesdropper, who's trying to listen in and snag that key.
And this is where things get really weird, in the coolest way possible. It all comes down to a fundamental rule of the quantum world. You can't look at something without changing it. The very act of observing it messes it up. So if our eavesdropper, Eve, tries to peek at the quantum key Alice is sending, she'll disturb it, and she'll leave behind undeniable fingerprints. There's just no way to snoop without getting caught. Here's a super simplified look at how this plays out. Alice sends a stream of these quantum bits, or qubits, over to Bob. Afterwards, they just get on a normal public phone line, nothing fancy, and they compare some notes. Now, if Eve was listening in, her snooping would have created a bunch of detectable errors. Alice and Bob would spot those errors immediately, throw the key away, and say, nope, the line's not secure, let's try again.
Okay, so we've got two really powerful but really different solutions here. On one hand, you have a software fix built on new math. On the other, a hardware solution built on pure physics. So let's put them head to head and see how they stack up.
And this table really lays it all out, doesn't it? PQC's security is based on these super hard math problems. It's what we call computational security. It's strong, but it's still an assumption. The huge plus? You can roll it out as a software update. QKD, though,
Its security comes from the laws of physics. It's unconditional. But, and this is a big but, it requires a whole new hardware infrastructure. We're talking new fiber optic cables, special photon detectors, the whole shebang.
I know. A lot of this can start to sound like pure science fiction, but the race to actually build a quantum computer powerful enough to do all this, oh, it is very, very real. So let's take a look at the major players who are leading that charge.
Okay, so two of the heavyweights in this ring are definitely IBM and Google. And what's fascinating is that they're taking pretty different paths. IBM is all about scale, just pushing for more and more qubits, like with their Condor processor that broke the 1,000-qubit barrier. Google, on the other hand, is really zeroing in on quality, hitting huge milestones in something called error correction, even with a smaller number of qubits.
And when I say ambition, I mean it. The scale they're talking about is just staggering. IBM's public roadmap isn't aiming for a few thousand qubits. No, they're targeting over 100,000 of them by 2033. That just shows you the insane momentum and, frankly, the money that's pouring into this field right now.
This quote really nails the state of the race, I think. You could say IBM is winning on sheer size and on making their tech available to researchers today. But Google is winning on quality with its error correction. And honestly, that might be the more critical piece of the puzzle long term. Here's why. Qubits are ridiculously fragile. The tiniest disturbance can ruin a whole calculation. Error correction is the magic that shields them and fixes mistakes on the fly. You absolutely need it to build a machine stable enough to actually run something like Shor's algorithm.
So where does all this leave us? What's the big takeaway? Well, it's pretty clear this isn't an either-or kind of deal. PQC, that's our practical right-now defense. It's the software patch we can deploy today. QKD is the bigger, more revolutionary dream for tomorrow, a future with a truly unconditionally secure network, but one we'll have to build from the ground up. And all of this leads to one final and pretty urgent question. The code breakers, they're getting closer every single day. The technology is moving at a breakneck pace. So it's really not a question of if anymore. It's a question of when. And as that clock keeps ticking, you have to wonder, are we building our new digital shields fast enough to withstand the storm?